Welcome back to Non-Equilibrium Thermodynamics, class number 6. So we've been talking about thermodynamic variables, and we've talked about Euler equation, which is the integrated form of the first and second laws of thermodynamics put together. We've talked about the Gibbs-Duhem equation and how this allows us to reconstruct the fundamental relation from limited knowledge of equations of state. And now we're going to go into another topic in basic thermodynamics. And as I said, we need to get a good foundation in thermodynamics to understand non-equilibrium thermodynamics. We're not going to spend all of our time here. We've only got what I hope are two more lectures beyond this one in the basic thermodynamic concepts, 7 and 8. Lectures 9 and 10 will deal with statistical mechanics, actually 9, 10, 11, and 12. Then we're going to talk a little bit about kinetic theory, the Boltzmann equation in particular, for 3 or 4 lectures. And then after that, we get about the midpoint, we get into what is the heart of non-equilibrium thermodynamics, um, talking about Onsager principle, talking about entropy production and things like that. But this is the foundational topics that we need. Today we're going to talk about Legendre transforms and Helmholtz free energy, which is perhaps the most famous or well-known Legendre transform of thermodynamic variables, and the one that we're going to use most often. I would say there's some other of these transforms that are used commonly in thermodynamics. The Gibbs energy, or the Gibbs free energy, and also the what is the other one that I'm missing? The enthalpy function are also what I would call thermodynamic potentials that are obtained through Legendre transformations. But we're not going to be using those so much in this course, and so we're only going to focus on the one that we're going to use, namely the Helmholtz free energy. What is a Legendre transform? So here's a little brief introduction to this topic. So suppose that f is some function. Let's just take it a function that's real valued from an interval. Suppose that it's continuous at least. Then for every p in CD, another interval, doesn't have to be the same as this one, but it might be, we're going to define a function called f star, a function of p. And it's going to be defined for every fixed p, we're going to take a supremum to calculate this object. So fix that value of p. For each fixed value of p, then it's the supremum over x in the original interval AB of the quantity x times p minus f of x. Okay, that'll give you a value, and that value, of course, will change every time I change the value of p. The function f star from C to D, CD to R is called the Legendre transform of f. Now, in some cases, the Legendre transform keeps all the information of the original function f, and that's the case we'll be interested in here for our thermodynamic change of variables. Suppose that f, and I'll give you precisely the case where that is so. So suppose that f is a C2 function, and f double prime is always greater than 0 for every x in the range, or sorry, in the domain of f. So here we're limiting the domain to be the important stuff for us from the thermodynamics point of view. That's the one that we'll be commonly using. So let's just stick with that. I could make this domain a little bit, I could make it bigger if I needed to. So uh, we're going to suppose that f double prime is greater than 0. This just means that f is a convex function. Then for all p in the range of f prime, why are we taking p from the range of f prime? That seems strange. Well, that's the natural domain of this Legendre transform. Okay, so p is in the range of f prime for some reason. Okay, look, we'll get back to that in a minute. F star of p is equal to x sub p times p minus f of x sub p. But what is x sub p? X sub p is a unique number. Can you guys still hear me? Okay. Is a unique number in 0 to infinity that is the solution of this equation. F prime xp is equal to p. F prime of xp is equal to p. So this guy is in the range, as we said from the offset, is in the range of f prime. Okay. That means that we may be able to, well, we should be able to find at least one value that gets mapped to P because it's in the range of f prime. But the fact that it's unique stems from the fact that this function is a one-to-one function. We'll get there in a minute. Okay, so the nice thing here is that we've defined this object generically above, but it has a unique definition and it's always given by this very simple, well, simpler formula. Okay, so this generic formula reduces to this very specific formula in the case where f is a convex function. So let's prove this. Suppose that p is in the range of f prime. F prime from 0 to infinity into the range of f prime is a one-to-one onto function. So why is this the case? Well, if I look at the derivative of f prime, that's the second derivative of f, and that's always a positive function. That means that f prime is an increasing function from its domain into its range. Therefore, we have a one-to-one onto function from 0 infinity into the range of f prime, and that means we can invert such a function, right? A function that's one-to-one onto its range is invertible. Therefore, for every p in the range of f, there is a unique pre-image. So sometimes this is called the image, this is the pre-image. There's a unique pre-image from the domain such that f prime xp is equal to p. Okay? And that just follows from the convexity of the original function f. If f prime, right, f prime, if we look at the second derivative of that, if that's always positive, then this function is increasing. And of course, it's a continuous function. It's differentiable. And that all follows because we're assuming that the original function is a C2 function. Now, let's fix P in the range of f prime. We know that, well, we don't know what the range of f prime is a priori. We're just going to assume that it is something available to us. Now let's use Taylor's theorem. So for every x, and where's this x coming from? This x should be somewhere in the domain of f. For every x in the domain of f, we can expand this function around this expansion point that we just conjured up. If we fix p, we know that there is such a point called xp, and that's going to be our expansion point. So let's do the Taylor expansion of f of x around this expansion point. What do we get? So by Taylor's theorem, it's going to be f of xp plus f prime of xp, but we know that f prime of xp is just equal to p times the difference, x minus xp, plus 1/2 f double prime of some point between x and xp. And we're going to call that psi p. Times the difference, x minus xp squared, quantity squared. So this is Taylor's theorem up to the second order. And right, so what do we have? What we're going to do is we're going to use the definition that we had up here. That involves this function or this difference of objects, arbitrary x from the domain times p. P is just some fixed number minus f of x. So notice we now have this Taylor theorem. We have those objects here, f of x and p times x. So I can arrange that information on one side and I get some other information on the other side. X p time minus f of x. So there's xp f of x. Let's just move that guy over here and take all the other things that are in this and throw that to the left-hand side. So that allows us to solve exactly for this in terms of what we have from the Taylor expansion. So the first thing we notice is that we get a lot of terms which don't depend on x when we do this expansion. So I'm going to leave the algebra up to you. It's very simple algebra. We get or times p minus f of xp minus this object here. So notice that this object does not depend on x at all, right? We're souping over what? We're souping over the domain of the original function x. Now, what do we have here? We have 1/2 f double prime of x or psi p times x minus xp squared, quantity squared. So notice that when we soup, we take this supremum here, this object here should vanish, right? When we take the supremum, what does this function look like? It's going to be a function which is shaped like this, and it should be exactly equal to zero or at, well, let's say at its maximum whenever x is equal to xp. So this guy completely vanishes when we take the supremum. This doesn't depend on x at all. So when we take the supremum, this term goes away. And all that we're left with is this. But that's exactly what we wanted to demonstrate, that when we take the supremum of this object using Taylor theorem, all that survives are these terms. Okay, so that shows that for a convex function, we get a simplification of that original formula, and it's just following from Taylor's theorem. And this is our expansion, or this is our new formula. So this is the Legendre transform, and we have a nice, simple, explicit formula that we can use. We don't have to use this more complicated object. Now, that doesn't explain yet why this function is at all interesting to us, this Legendre transform. We're going to get to that point momentarily. We need a couple more facts about this thing first. So if, again, f is a C2 function from its domain into R, real valued function, that is convex, then the derivative, this is just the derivative of the Legendre transform function f star, we have a formula for that. It's precisely equal to the inverse function of f prime, the inverse of the f prime function. So remember we said f prime is an increasing function. It's invertible from its for the function that takes its domain to its range is an invertible function. Whatever that function is, we don't care. We just know that it exists and it's unique. And so that turns out to be the derivative of f star prime. Okay. The other thing that we can find with this calculation is that the second derivative with respect to its variable p. Okay, so the variables of the f star function are this p. P comes from the range of f prime. No, make sure that you understand that when we restrict p to be from the range of f prime, this formula, whatever it is, has to make sense. And of course it does. Okay, so this is what we want to prove, and we want to also prove this. So let's see if this can be done. At least I claimed or thought it could be done a few days ago when I wrote up the notes. So this function, f prime, is an increasing function. It's one-to-one onto from its domain into its range. We don't know what the range is, and we'll see from an example that the range of f prime certainly doesn't have to be the same as its domain. Well, what do we know about the inverse function? The inverse function is satisfies an inverse relationship with the original function. This is what it means to be an inverse function. The only weird thing here is that we're dealing with the prime function rather than any other function. You might think that we should be working with the inverse of f, but it turns out That's not what we need to be working with. It's f prime. And this holds true for every value of p in the range of f prime. So this is the inverse relationship that we want to use. And now let's take let's examine what we mean by the the derivative, or what should be the derivative of the inverse of f prime. Um, all we know right now is that this should be a continuous function from the range of f prime into R. We don't know where it's actually, I think, let's see, do we know? We don't know exactly where its what its range is, but we do know what its domain is. Furthermore, we have we can come up with a formula for this guy. It's not too hard. Let's see if all this makes sense. So let's take the p derivative. Okay, so set this information aside for a moment. We're going to try to show that these two objects are the same. Let's take the derivative of this object first. Okay, so the derivative of p, or with respect to p of f star p, what is this exactly equal to? Well, we have a formula here, right? There's our formula, and we need to take the derivative of that formula with respect to p. This object here is really nothing more than the inverse of the prime function. So the reason why I made the observation that this actually is differentiable is because we're going to have to differentiate it down here. So fill that guy in, right? And what do we have here? Okay, we're going to have to differentiate this function as well. This function is f composed with the inverse of f prime. So you might be tempted to say, well, that's just equal to p, but it's not. It would be p if this was the prime function out here, but this is the original function f. So we're going to have to differentiate this guy as well. Okay, so we've got to use the product rule here because these are two functions of p. This is going to require a chain rule, right? All right, so product rule, what does that give us? Let's take the derivative of this guy first, times p. So I don't know what that thing is yet, but let's hold on to that. And the derivative of p with respect to p, that's just 1, and that leaves this function back again. It's that thing there. All right, now what about this function? To do the chain rule, we're going to have to take the derivative of f with respect to its variable. Its natural variable is called x, so we need to take df dx, and then we have this inside, right? This is the composition. But notice that once I take the derivative of this thing on the outside, that is f prime, and I'm composing it with the inverse of f prime. This whole thing is then just p. Now I have to take care of the other piece in the chain rule. That's going to be the p derivative of what's inside. Okay. And I don't know what that is, but I don't care either because I'm going to have another one up here. So you don't know what that is. Just set it aside. This is going to be p times that derivative and a minus p times that derivative. And so I just get a cancellation of those two terms. And what's left is f prime inverse p, but that's the only thing left, so that must be the derivative, and that's what we wanted to show. Let's see. So now that this is established, we have the first, or sorry, the let's see. We want to show. Let's look at what we want to show. We want to show that the second p derivative of f star is always positive. So we took one derivative of f star. Now we have to take a second derivative of f star, and that requires us taking this second derivative of f star. That's going to be a first derivative of that function. Again, we said we don't really know what that function is, but now we can use the inverse function theorem, right? Since we know that this function here is an increasing function in its variable, then that means we know something about the inverse function as well. It's also increasing in this variable p. So this function has to be, we don't know what it is, but we do know that it has to be positive by the inverse function theorem. And so that says that the second derivative must be a positive function, and therefore we're done. So what is this saying? This is saying a couple of important things. We know the derivative of that thing, but we also know that this is a convex function of its variable. So you start off with a convex function f, you take the Legendre transform, and you get another convex function of a new variable called p. But that means that we can take the Legendre transform of the star function. Then the question is, well, what is the derivative of the star function? Let's do an example and see what I'm not going to actually take the the Legendre transform of the Legendre transform, but I will give you the answer. Let's take a simple example here. So suppose that f of x is equal to e to the x. We can restrict the domain if we needed to 0 to infinity if you wanted to, but we don't have to. That was just for our thermodynamic purposes. And the natural domain for this function is, of course, all real numbers. This is easy because the first and second derivatives are the same as the original function. The first derivative is e to the x, the second derivative is e to the x. Both functions are, of course, positive. The second derivative is the one that we're most interested in, and that, of course, is a positive function. And so f is convex. We know what this function looks like, right? Convex function means it's smiley and more of a smirk, I guess. F of x is a convex function. Now, what we need is the derivative function, right? That was very important for defining Legendre transform. That's f prime, of course. The domain of f prime in this case is the same as the original. We also need to know what is the range of f prime. That's going to be the same range as the original function, f. That's 0 to infinity. So the f prime is here, of course. That's e to the x. I could do e to the minus x as well, and so I'll leave that as an exercise for you. That's also a convex function. You can take the Legendre transform of that. The um, the inverse function, of course, is just the log. Notice that the original function f is an increasing function. The inverse function is also an increasing function. We use that in the proof of the last result. But this is just a log function. So this function is also f prime is clearly an increasing function, as we've said before. The function g, which is the inverse of the f prime function, is the log. That's an increasing function. So let's see what we need to do to compute our Legendre transform. So our formula for Legendre transform is just this, right? xp times p f of xp. Now here I can just realize xp, that just means xp is nothing more than the inverse of the prime function, f prime function of p, right? Did I do that right? Yep, that should be right. Um, and so that's what goes here and here. So f star p, that's just going to be g of p. That's just the label I gave to the inverse function just to keep things from getting too messy. I didn't want to write this again and again, so I called it g of p above. G of p times p, f of g of p. Well, this just gives log of p times p minus the exponential of log of p. That's just equal to p. And so this gives us a nice clean formula for the Legendre transform of the exponential function. Now, this function is going to pop up again and again in our discussions. This is called, it has a very important function in thermodynamics and a very important, well, and therefore it's got its own name, as most important things do. It's called the ideal gas function or the ideal gas model. Now, when we were dealing with the ideal gas law for gases previously, we didn't see this function coming up, but it does have a connection to ideal gas, and we'll see this again and again. But in any case, this function is important enough to get its own name. It's called the ideal gas model. More on this later. Now, this is the Legendre transform of e to the x. A little bit weird, right? You take the Legendre transform of an exponential, you get a log. If we take the Legendre transform of this guy, what do we get? Well, we said that you can take a Legendre transform of the Legendre transform because it's also a convex function. By the way, what does this function look like? What does this function look like? It looks something like that, right? So that's what this ideal gas law function looks like as a function of p, of course. Take the Legendre transform of that, you get what? You get another convex function. That has to be the case. But it turns out that when you take the Legendre transform of the Legendre transform, you always get back to the original function as long as you've started with a convex function to begin with. So in this case, we take the Legendre transform of Legendre transform, we're going to get back to e to the x. We're going to see that this is precisely true in general with the next theorem. And I'm not going to prove this theorem in class. I think I'll just leave this for you to read, but let's go through the statement of it very clearly. Suppose that f is a C2 function from 0 infinity into R. Again, the range is not so important. I've just kept this to be that range, which is typical for us for thermodynamic variables. Let's suppose that f is a convex function. Its second derivative is always positive. It's a C2 function. Its second derivative is always strictly positive. That means its first derivative is an increasing function. Then f star is also a C2 function in the range, or sorry, C2 function whose domain is equal to the range of f prime. That's a bit strange, but that's what it is, and that works for us. Its second derivative is always strictly positive. We've already shown this with a theorem. Um, if you look at the last example, you can show this as well. We didn't compute the derivative, the second derivative of that ideal gas model, but you'll find that this holds true. And if I take the star of the star function, I always get back to f. Okay, so this is something I claimed with the last example, and is true in general. So in other words, the Legendre transform is what we call involutory. It means it's its kind of own inverse operator, and therefore it's completely information preserving. What does this mean? Well, this means that we don't destroy any information by taking the Legendre transform. We could always get back the original information of the thermodynamic function after taking Legendre transform. So, right? Doesn't that make sense? If I take the transform of an object and then take the transform again, and I get back to the same object, then that must mean that I haven't destroyed any information in that process. Well, what that means is that if I have a thermodynamic variable, like say the internal energy function, and I take a Legendre transform of that, and I take another Legendre transform, I get back to the original relation. This relation we called the fundamental relation of the problem. And the fundamental relation says that, or means, or gives us every thermodynamic piece of information that we need for the system. It doesn't hide or conceal any of it. Um, So that means if we transform this, we might get something different in the transformation process, but that transform that we get should preserve all of the information of the system originally. It doesn't lose any. So the question is, well, why do you do the transform in the first place? So this is what I aim to show with the Helmholtz free energy. So it's a particular Legendre transform and a useful one at that. So as I said, we won't go through the proof of this for the sake of time. We'll skip it, and I want you to read through the proof of this and as an exercise and make sure that it all appears correct. So the question, therefore, after reading the proof is why is this Legendre transform at all useful in the world of thermodynamics? And this is what we want to talk about next. So in the next part of the lecture, we want to see why Legendre transform is useful to us in thermodynamics. So let's start off with variables that we're used to seeing. Suppose that we have the fundamental relation given in terms of the internal energy. So that means the internal energy is completely specified in terms of the entropy, the volume, and let's say we're working with a unary material, so it's the number of moles of our uh, uh, number of moles of the atoms of the gas, let's say, that we're working with, or the fluid. Now, the combined first and second laws, that's usually written in differential form like this. du is equal to TdS minus PdV plus mu dN. So I want to harp on this point once again. So what this means simply, this is just an application of the chain rule, and there's no more content in that than there is in a statement like this. It simply means that this object here is the first derivative with respect to S. This object is the first derivative with respect to V. And this object is the first derivative with respect to N, right? First partial derivative. But those functions happen to be or play a very important role for us. Temperature minus the pressure, the chemical potential. So these variables are called conjugate variables. They're conjugate to the variables that they sit beside in this relation. So T is a conjugate variable to S, minus P is a conjugate variable to V, and mu is a conjugate variable to N, the number of moles. Why are they called conjugate variables? Well, it turns out in thermodynamics, we are allowed or able to switch between an original variable and its conjugate. And so that's what I want to show you. There are all of these transformations that you're allowed to do or able to do, one of which is called the Helmholtz free energy. And this allows us to switch variables, swap variables. We'll see how to do this. But for now, let's just look at this in sort of usual terms. If we have the energy function, then its primary variables are S, V, and N. These are the primary thermodynamic variables. The conjugate variable to S is T. Conjugate variable to V is minus P. Conjugate variable to N is mu. That's what I said just above. What about if we had the entropy function as a function of internal energy, volume, and number of moles? Then the variables would be U, V, and N. And the conjugate variables would be as follows. Conjugate variable to U is 1 over T. Conjugate variable to volume is pressure over temperature. And the conjugate variable to N is minus the chemical potential over temperature. Okay, so make sure you understand it's whatever sits beside this variable whenever I write the combined first and second laws. So that would be ds tilde is 1 over T du plus P over T dV plus minus mu over T dN, right? So we showed these relations. If I start out with these relations, then these relations follow by inverse relations. And so 1 over t sits next to u, so that's its conjugate variable. P over t sits next to v, so that's the conjugate variable there, etc. So just make sure you understand that in this formulation, it's not the temperature which is conjugate to U. It's 1 over the temperature. It's not pressure which is conjugate to V. It's pressure over temperature, etc. Now, I'm going to define an object. Now, remember, U, what do we know about the U function? U is a U is a convex function, right? It's a convex function of its three variables. But really, we are only going to care about the fact that it's a convex function of these two variables here, okay? Or this variable here. Now, I'm going to define I'm going to use Legendre transform. It's in a slightly different form than we had above. It's basically, I'm using minus the Legendre transform. So let's go to what we had above. And what's important is the second formula, this guy here. So f of p, if we want to take the Legendre transform of that guy, then I should take xp times p minus the original function. So the original function that I'm taking the Legendre transform comes in this slot here. So whenever I define the Helmholtz free energy, we have it flip-flopped. In fact, basically I've just multiplied by a minus sign. So why did I do that? The reason why I did that is just because it turns out that that's more useful to us. So we're defining it with the minus sign. But most all of what I've said here up above still pertains. Okay, so let's see here. Oh, we go. Right. So it's T times ST minus U. That's how, sorry, U minus TST. So we're defining it a little bit backwards, but it's still a Legendre transform. And if you're puzzled about that, have a look at it and think about what we're doing. All right, so U minus TST. This is how we're going to define the Legendre transform. So, or if, you know, we've introduced all these tildes and let them float around. In the thermodynamics literature, none of this appears. So they would just write this as F is equal to U minus TS. Okay, U minus TS. So let's see why and how this defines the Legendre transform. And as I said, so the Legendre transform is going to preserve thermodynamic information for us. It's not going to destroy it. So, but let's drill into this definition. Suppose that all of the thermodynamic potentials hold. So that means we can always assume that U is a convex function, S is a concave function. Both are increasing functions of their first variable, and et cetera, et cetera. Um, Assume that the material in question is unary. This just keeps the discussion simple. So we're not talking about like 30 variables here, only three. So the definition of the Helmholtz free energy is as follows. First, note that what we're doing is we're claiming that I can look at the Helmholtz free energy as a function of T, V, and N. This is different than anything we've done yet. So we've looked at previously, U has been a function of S, V, and N. And S has been a function of U, V, and N. But nowhere before have we written something as a function of the temperature, okay? Where the temperature is an independent variable. Now we're going to define something where I'm going to claim that the temperature is indeed going to be an independent variable. So we've got to be careful in our definition here. And this is just, like I said, it just involves a Legendre transform. So remember I said this is a minus of a Legendre transform. We're switching to a new variable here. So this variable t must be like the p variable that we had previously. So the p variable was in the, where was it? It was in the range of the derivative. Is in the range of the derivative. Well, this t is in the range of the derivative for the u function. And so you can see now why this is minus a Legendre transform. Okay, so let's get into it a little bit further. So we're switching from variables of s, v, and n to t, v, and n. So this is equal to, by definition, the u tilde function, so the internal energy function. This is playing the role of little f in the previous definition. This should be a function of st, v, and n. I'm going to get to what st is in a moment, minus t times st. Now, st itself is going to be a function of a few variables, namely t, v, and n. St is going to be the unique solution of this equation. Okay, it's going to be the unique solution of this t equation. This is the temperature with respect to the internal energy definition. STVN, Vn equal to t. So if you give me a value of t, it has to be in the range of the temperature function. T has to be in the range of the temperature function. Then I claim that I can always find a value of the entropy which inverts that function, which inverts this function here. So that means that S is going to be dependent on T, V, and N. You can think about it this way. I start by fixing V and N, and then I let T be in the range of the temperature function. Then I can always find an entropy which maps that temperature function, or which gets mapped by the temperature function, I should say. Always find an entropy that gets mapped by the temperature function to that value of T in the range for fixed values of N and V. All right, so we're going to see if this function is useful or not. Now, in the thermodynamics literature, they don't define the Helmholtz free energy this way. And the reason they don't is because they don't care about the mathematical analysis. That's okay. They're trying to make progress in physics. We're trying to understand the progress that has been accomplished in physics from a mathematical point of view. So that's why we're defining it in this very complicated way. As I said before, physicists would simply write, I'm going to define this as being equal to this object here. That's how the physicist would write it. But the mathematician has to make sense of that. And they would claim, well, this object here is now a function of t, v, and n. And the mathematician scratches his head and says, how is that possible? Well, this is the definition which makes all that so, okay? Makes all that possible. So now we can make a definition, no problem. Mathematicians are good at making definitions. The question is it worth anything? Does it give us anything useful? Well, we're going to give it a name like it's going to be useful to us in the future. We're going to call this the Helmholtz free energy. Keeping with what we've been doing so far, I've been defining things and then giving their mathematical significance much, much later. And that's going to be the case here. You have no idea why I'm introducing this thing called the Helmholtz free energy. I hope to prove that it's useful with some later results. Now, let's do things formally. Let's do things formally at first. So if I have the definition that I showed you above, so formally we have, if I start with, let's make a little bit of room. I want to add a bit of information here. So we start off with this definition, right? F tilde is equal to U minus T times S. Now let's just pretend we can take a differential of that business, okay? If I can take a differential of that, then I'm going to have to apply a product rule to this guy. So I'll take the differential of F, and so I get differential of U. If I take the differential product, then I get I have to use a product rule, and that is minus S dt. The usual thing in thermodynamics literature is to write the differential second. Okay, so I'm really taking the differential of T first. S dt minus TdS. But expand this. We know this from the first and second laws. That's just TdS minus P dV plus mu dN. And what do we get? What happens is this term and this term, at least formally, cancel. And I replace what was here in the U variable with minus S dt. This is the one that survives. So what this is saying is that you might start off with these three variables, S, V, and N, and with these three conjugate variables, T, minus P, and mu. But what this suggests by doing this Legendre transform, or minus the Legendre transform to be truly, to be honest, is we change variables in this location so that now T becomes the primary variable and minus S becomes its thermodynamic conjugate. The other two variables stay the same. The other two variables stay the same. Why is this useful to us? Well, it may be useful to us because we may have, or think about this experimentally. Is it possible to control the entropy and the volume and the number of moles? Well, I know how to control the volume in an experiment, and I think I know how to control the number of moles in an experiment, but I don't know anything about how to control the entropy in an experiment. Let's suppose I want to keep an experiment at constant entropy. Is that possible to do? So I don't know how to do it, and many experimentalists didn't know either. And so they were searching for a way to transform and get rid of this variable, and therefore switch to a new thermodynamic potential away from U and to one where they had variables that they could control. The temperature is a variable that you can control. So if I want to switch to T, V, and N, three variables where I can control, the I can turn the dials in a thermodynamic experiment, then that means I have to switch to something, a new thermodynamic potential. And the one I'm going to switch to is F. Remember, this is defined as minus the Legendre transform of U. Well, I get rid of, or I get this new thermodynamic variable T, but I gain this conjugate variable minus S. So the question, is that useful to us? Well, at least from the outward appearances, now I have three thermodynamic variables that I could control. I think I know how to control the temperature because I can dial a thermostat up and down. Now it isn't clear how you can control the temperature. Um, so I want to make that I want to make that statement from the beginning. Now, most of us have become familiar with adjusting temperature because we're used to having a thermostat in our home or our apartment. But even that is a deep and interesting concept that we won't be able to touch on too much in this class. But just take my word for it that temperature is a controllable thermodynamic variable, whereas S is not. So if I change from this thermodynamic potential to this thermodynamic potential, I may have gained something. And it turns out you actually have. So let's, as we usually do an example to see what we're talking about and hopefully have a useful example. I'm going to throw in the example that we've used again and again over time. That is this thermodynamic relation involving this cube root. S entropy fundamental relation as a function of U, V, and N is given by this equation over here. Of course, I can invert this pretty easily for the U variable. So instead of thinking about entropy as a function of internal energy, volume, and number of moles, I can look at the internal energy as a function of entropy, volume, and number of moles. The temperature function Well, we can get this in one of two ways. Remember, we can take the derivative of the internal energy with respect to S, and that gives us the U version or the internal energy version of the temperature. That's pretty easy to do, right? If I take the derivative with respect to S, I get 3S squared V naught theta over NV R squared. And these three numbers here, V naught, theta, and R, are of course constants. This function and this function are both homogeneous of degree 1, easy to check. This guy is homogeneous of degree 0. I can also calculate the temperature by taking the derivative of S with respect to U and inverting. That gives me the entropy version of the temperature. And we've done this calculation a few hundred times now. But what I do want you to do as you read through the notes is check these things so that so that it all makes sense. Make sure I'm not coming up with any silly errors. I claim that this temperature is given by this relation as a function of U, V, and N. Now, these two temperature functions should be equal to each other in some sense through inverse relations involving the entropy and internal energy. I'll let you check that. Those relations are precisely these here. I didn't check them for this particular case, but I believe we checked those previously in other examples and other lectures. Well, we're trying to construct a new thing for this model called the Helmholtz free energy. Whether or not it's useful, I don't know. So let's fix V and N, and we're going to fix T, a value of the temperature in the range of the temperature function. So if I fix a value of T um, in the range, I want to know, is it possible that I can invert this function? Um, and it turns out the answer is yes. I want to invert this function and find a function of S as a function of T, V, and N. So here's our temperature function. Now we're going to set this equal to a specific temperature. Of course, the temperature has to be positive. It has to be a positive number. So if I set this equal to T, okay, we're going to set this equal to a specific value of T. Can I invert that? Well, if I do that, then what does it mean to invert that? I want to know what this value of S is as a function of T, V, and N. And that's the function I called S subscript T V N. Why did I give a subscript? I'm getting, I'm running out of usable notations. I could have said tilde tilde, but that didn't work for me, so I called it subscript. This seems to be okay. So I want to solve for S in terms of T, V, and N. Is this possible? Yeah, it's possible. Just solve for S. This involves just taking a square root. Well, throw everything that you see here to the other side and then take square root. You get this function. So notice that this is a function of T, V, and N. So what was our definition? Our definition of the Legendre transform said you had to get this function, you need S sub T, and you're going to put that in the first location of the energy function. That's the definition. Minus T times that same thing, ST. So U of ST, V and N minus T, ST. That's the definition. Weird definition. I understand that, but that's what it is. Now, what is this function? The I have the relation for U up above. And so if I put this function in there for S, what do I get? Well, U as a function of ST, V, and N, that's going to be ST cubed, okay, times all the other stuff. That's all the same. I have an expression for ST. If I cube that, then I get 3/2 power of this stuff times all the rest of the stuff. Well, all that really matters here is that now I have a closed expression for this. Okay, if I have that, I'm going to sub it in down here for my U term, U of S T V N. That's that. Minus T times ST. T times ST. Remember, in our definition of Helmholtz, we're taking minus Legendre transform. Not a big deal. It does change some of the facts, but why didn't I give things in terms of minus the Legendre transform? It's just because typically the facts are all given in terms of the former rather than the latter. So you can go through that and see what's different. Okay, now I should be able to simplify. This term here is the same as this term here, except for the powers are a little bit different. So I'm going to pull out the common power, and reserve whatever else is left. Okay, so do a little algebra, you get this, and there's that common factor. So pull that out. What you're left with is this term minus this term times that common factor, just using the distributive property. I can do a little bit more solving. Basically, I can get down to a fairly nice expression for f, which looks like this. Okay, so what, right? You're probably saying that to yourself right now through your yawns and your boredom. What? Who cares? I've successfully transformed the energy function, the fundamental energy relation from a function of S, V, and N to another function that's a function of T, V, and N, and a little bit of dyslexia here. There we go. So transform the U function as a function of S, V, and N to the Helmholtz free energy of function of T, V, and N. Now, I hope you believe what I was saying before, because it is true. I start off with U, it's a convex function. I get a new function through my Legendre transform here. Now, maybe a little bit different because we're using minus the Legendre transform. So I want you to go through as an exercise and say, well, what are the properties of minus the Legendre transform? In any case, I've got a new thermodynamic function which I claim has lost no thermodynamic information. Okay, it's got all of the thermodynamic information that it had before, but it's now a function of T, V, and N. Is that useful? We'll see. We'll see. Let's take the derivative of this function. What did I say before? I said I made a claim. I made a claim that just the physicist sees this right away. It's patently obvious that the differential of f is equal to that. And they say to themselves, well, of course, minus s is going to be the variable that's conjugate to t. The mathematician looks at the more mathematical version of the definition and says, well, let me prove that. So what is the mathematical definition of this conjugate variable? We have to show, right? We believe that this is now a function of t, v, and n. So what we have to show is that the derivative of f, the partial derivative of f with respect to t, must be minus s. Let's see that that is the case. So there's our expression for f. And the reason why I separated t here as a separate variable is because I want to do this differentiation with respect to t. So let's do the differentiation, the partial derivative of f tilde with respect to the temperature variable. And notice here, I'm not writing this as t sub u, t sub s, anything like that. That is unnecessary. This is now an independent variable, so I can call it whatever I want. Take the derivative with respect to t, what do you get? Clearly, this is going to become, this is treated as a constant. I'm going to have 3 halves t to the 1/2 power. The 3 halves cancels with the 2/3 in front. I still have the minus sign. Now I have the square root of t. This 1 cancels. I can bring that into the inside, right? Bring that into the inside. But let's make an observation here. What I want to show is that the stuff that lives over here, all this stuff over here should be minus s somehow. Minus s. Okay. Well, remember what the internal energy version of the temperature looked like. It was this function here. And remember what ST looked like. ST was equal to, well, we had the relationship above. ST is basically proportional to the square root of temperature. So what you can show is that this object here is just ST. Okay, you can see that pretty clearly here. I probably should have just written ST from above. Do we have ST? Yeah, it's just this object right here. It's actually simpler than what I've written all this. I don't know why I went through all this business. I just was, I guess, convincing myself once again. But that's just minus ST. So the derivative of F with respect to T is just minus ST. In fact, maybe I'll clean that up here. So make it even more obvious. Okay, so ST, we already had a formula for that. Why not use it? And of course, we observe right away, that's just ST. This is just a minus 1. And so we have it right away. Okay, the derivative of F with respect to T is minus ST. Now, the next thing I would want to know is it possible to show that the derivative of F with respect to V is equal to, what should that be equal to? Let's check our physics quick calculation here. Should be equal to minus P. And the derivative with respect to N should be the chemical potential. But I have to think about how that would be expressed. How would that be expressed in our sort of mathematical way of thinking? First, before I get on to another example, which is going to make this clear, let me state a theorem. I can define the Helmholtz free energy in a couple of different ways. And another equivalent way for finding it, at least for the unary case, is as follows. F of T, V, and N. So notice this is exactly the same function as above. I'm saying that this is an equivalent definition or means of finding the Helmholtz free energy. It's equal to UT, whatever the heck that is, minus T times S tilde. This is the fundamental relationship for the entropy of UT, V, and N, where UT, a function of V and N, is the unique solution of this equation. So now I use the entropy version. Notice I'm using the entropy function. So I'm going to use the entropy version of the temperature to invert this relationship. So this is going to be naturally a function of u, v, and n. If I fix t in the range of the temperature function, then I should be able to invert this for the u function. And that's the reason is due, why you can do this is due to convexity. Okay, so I want you guys to have a look at that and see if you can prove that we gain this or obtain this equivalent version of the definition of the Helmholtz free energy, but from the perspective of using the entropy function rather than the temperature function. See if you can prove that. What I want to get onto before where our time is up here in 6 minutes is another example. I'll run through the details of this. Once again, I'm going to go through the details a little bit fast, and I want you to come back and confirm the details. So this is the fundamental entropy relation for the monotonic ideal gas that we saw before. So that's what we actually calculated this from what? From two equations of state, one involving the temperature and one involving the pressure. we calculated this entropy law. There are a bunch of constants here. Don't worry about those. What you really are worried about is how this thing depends on N, U, and V. Okay. N is there, U is here, N is also here. Everything else is a positive constant in sight. So we're going to calculate this in the entropy way. So this is the calculation of the Helmholtz free energy using the entropy function. Well, that means I want the temperature in the entropy formulation. How do I get that? You take the derivative of S with respect to U, and then you invert that. The derivative of S with respect to U is going to be 3 halves NR over U. So if I invert that, I get the S temperature is equal to 2/3 U over NR. 2/3 U over NR. That's the temperature of an ideal gas in the entropy relation. It's exactly the same as the temperature function. It has exactly the same thermodynamic content as the temperature obtained by differentiating the internal energy function, the internal energy fundamental relation. I can invert this function right away. If you put a t over here, I can invert this for u, and that thing is what we call ut. Okay? Or I could say ut as a function of n and v. It's actually a function of all three variables, t, v, and n. Okay? But it's easy to invert this. Okay? So I'm just inverting that function right there. Okay? And the inverted function is called utnv. Okay, so that's that. And now by definition, or not by definition, by the last theorem, so this should be equal to ut minus t times the s function, right? Times the s function, but where ut replaces the internal energy. Okay, so I'm not going to go through all the details of this. I'm simply going to ask you, please check this. You should get a function of t, v, and n out in the end. Okay. And all I'm doing here is, again, I have a functional version of this guy relation. Wherever I see u before, I'm just going to plop that guy down. So u appeared in only one place, and it was exactly that spot right there. I'm going to define a new characteristic temperature. This makes life a little bit easier for me. And that characteristic temperature is basically everything that appears here which is not equal to T. So you can check that that stuff actually has units of temperature. Okay? It has to have units of temperature. So I define a new characteristic temperature called T naught, and then F becomes this function of T, V, and N. So these are the first two terms. They don't change. And then this guy here is right here. And this is my new characteristic temperature that I just defined. Now, what are the so that's the derivative of F with respect to T. And what have we gained here? Well, we've at least transformed the internal energy, or if you want to think about it as the entropy, we've transformed those fundamental relations to a new fundamental relation which depends on temperature, volume, and the number of moles. I've gained a new independent variable. So, if that's the case, then our cheat sheet that we wrote above, the physics cheat sheet, says that the conjugate variables for these variables t, v, and n must be minus s, minus p, and mu. So in what way or in what sense can this be true? Well, if I take the derivative of this function with respect to t, you should be able to show that this is equal to minus s tilde ut v and n. This guy here is a function of t, v, and n. So that converts all this to a function of t, v, and n. Alternatively, that's exactly equal to minus st, v, and n. We actually showed this above. This we know to be true, but this is not something that we computed in this last example. Likewise, I should be able to show that the derivative of f with respect to t, sorry, this is not right. This should be v, and that should be n. Derivative with respect to v should be minus the pressure. This new pressure is now a function only of t, v, and n. Only of t, v, and n. Convince yourself of that by doing an example. And then finally, the derivative of f with respect to n, that's the chemical potential. And this is now a function of only t, v, and n. So I'm going to leave those as exercises, and that's where we're going to end for today.